Welcome to This Explainer. Today, we're going to demystify chemical energetics and translate those abstract, sometimes intimidating equations of thermodynamics into a highly visual, conceptual journey. If you've ever felt completely bogged down by the heavy math or the dense jargon in physical chemistry, well, you're in the right place. We're going to build a really clear, intuitive picture of exactly how energy flows through our universe. All right, let's dive right in. Here's a quick roadmap of what we're covering today. 1. System and surroundings. 2. Rules of heat and work. 3. Expansion and compression. 4. Reversible versus irreversible processes. 5. The laws of thermodynamics. And 6. Thermochemistry basics. Section 1. System and surroundings. Setting the stage. To really get a grip on thermodynamics, we first have to introduce our main character. We call this the thermodynamic system. It's really just the specific region of space or matter that we choose to investigate, right? Everything else out there in the universe interacting with it is the surroundings separated by a boundary. And to describe the state of our system, we use variables that come in two distinct flavors. First up, intensive variables. These stay exactly the same no matter how big or small your system is. Think about temperature or density. If you cut a block of iron right down the middle, its temperature doesn't suddenly drop by half. On the flip side, we have extensive variables. These depend directly on the amount of matter you have. Volume, mass, total energy. Those are all extensive. If you blow twice as much air into a balloon, you double its mass and its volume. Nailing down this difference is totally crucial for tracking our system's properties. Section 2. Rules of heat and work. The IUPAC conventions. Okay, so we've got our system defined. Now we need to know the strict banking rules it plays by when it's trading energy with its surroundings. Just think of your system like a bank account for energy. We mainly track this energy as heat and work, and the IUPAC conventions make this beautifully simple. Any energy deposited into our system is a net positive. So heat absorbed by the system or work done on the system gets a big plus sign. Conversely, any energy spent by our system is a negative. If the system gives off heat or has to exert effort to do work on its surroundings, its energy drops, so it gets a minus sign. Seriously, keeping this simple bank account analogy in your back pocket will save you from a ton of mathematical headaches later on. Section 3. Expansion and compression. The physical reality of work. Let's take this work concept out of the ledger and see what it actually looks like in the real physical world. Picture this. Our system is a gas trapped inside a cylinder, and sitting on top of that gas is a weightless, perfectly frictionless piston. This is pretty much the classic thermodynamic model. The piston's position is a tug-of-war between the external pressure pushing down and the gas pressure pushing up. If we drop the external pressure, say by taking some weights off, the piston moves up. The gas expands outward, doing work on the surroundings. Or if we add weights, it compresses inward, meaning the surroundings do work on the gas. By the way, this exact mechanism, it's literally the foundational concept behind how your car's engine works. Now, if we drop that external pressure suddenly and just let the gas expand in one sudden clunky step against a constant pressure, we get what's called a single-stage expansion. When we map this out, the work done by the system is represented by the shaded rectangular area under the pressure-volume curve. It's just an abrupt, spontaneous jump from point A to point B. But here's where it gets interesting. What if we slow the whole thing down? If we break that same expansion into multiple, smaller stages, gradually reducing the pressure step by step, that shaded area actually increases. And more area literally equals more total work output. Basically, by taking it slow and making the process more gradual, our system becomes more efficient. Section 4. Reversible versus irreversible processes reaching the limit. This brings us to a really massive concept in thermodynamics, the dividing line between an abrupt, irreversible process and a perfect, reversible one. Let's push that multi-stage idea to its absolute theoretical limit. Imagine expanding the gas through an infinite number of microscopic, incredibly slow steps, adjusting the pressure by just the tiniest infinitesimal amount each time. The entire area under the curve becomes completely filled in. This visually proves a fundamental, universal truth. Reversible, infinite-stage processes will always give us the absolute maximum possible work output from any system. So here's the takeaway. Reversible processes are these perfect mathematical ideals. The system stays in virtual equilibrium the whole time, and you can reverse the steps to put the system and surroundings back exactly how you found them. But real-world reactions, like a balloon popping or boiling a pot of water, those happen in sudden, finite steps. They're always irreversible. You can't just hit rewind without permanently altering the universe. Ideal reversible processes show us our maximum limits, but irreversible processes describe the wonderfully messy reality we actually live in. Section 5. Laws of Thermodynamics, the overarching rules. We've got the mechanics of our cylinder down, so now we are ready to zoom out and look at the absolute, universal laws governing energy across the whole cosmos. We actually start, funnily enough, with the zeroth law. Yeah, it was written after the first and second laws, but scientists realized it was so foundational it had to come before them. It just states that if System A is in thermal equilibrium with System C, and System B is also in equilibrium with C, well, A and B must be in equilibrium with each other. Sounds like pure common sense, doesn't it? But it's totally vital because it gives us the entire logical foundation for defining temperature. It's the reason thermometers actually work. Next is the heavy hitter, the first law of thermodynamics. The ultimate cosmic accounting rule. It demands that energy can never be created out of thin air, and it can never be destroyed into nothingness. The universe's energy ledger is always perfectly balanced. If energy vanishes from your system, an exact, perfectly equivalent amount has to manifest in the surroundings. No exceptions. And we can summarize that grand cosmic rule with one elegant little equation. du equals dq plus dw. Any microscopic change in a system's internal energy, that's du, is exactly equal to the heat exchanged, dq, plus the work done, dw. Remember our bank account from earlier? This is just the literal mathematical formula for calculating your balance. Now, obviously, most chemistry doesn't happen inside thick, sealed, rigid vaults. It happens in open beakers exposed to the constant atmospheric pressure of our Earth. So, scientists created a brilliant shortcut called enthalpy, denoted by H. It bundles internal energy together with pressure-volume work. And the beauty of this is that under constant pressure, any change in enthalpy equals the exact amount of heat absorbed or released. It's a lifesaver. Chemists can just track heat flow right on an open lab bench. Section 6. Thermochemistry Basics. Let's take these big, universal laws and apply them directly to chemical reactions and the slightly weird physical behavior of real gases. Okay, I've got a fascinating puzzle for you. Imagine a gas expanding into a lower pressure area. But here's the catch. Absolutely no heat is allowed in or out of the system. What happens to its temperature? You might assume it just stays the same, but the reality is way cooler. Two brilliant scientists, James Prescott Joule and William Thomson, put this to the test. They set up a totally insulated tube, so zero heat transfer, which we call an adiabatic process. Then they forced different gases through a fine porous plug, moving them from a high-pressure zone to a low-pressure zone to make them expand. What they found is now famous as the Joule-Thomson effect. At normal room temperatures, most gases actually chill out and cool down as they expand through this plug. But incredibly, gases like hydrogen and helium do the exact opposite. They heat up. It all comes down to a specific threshold called the gas's inversion temperature. Start above that temp, the gas heats up upon expansion. Start below it, it cools down. It's an amazing showcase of how internal molecular forces play by strict thermodynamic rules. When we visualize an adiabatic expansion, where no heat is exchanged, notice how intensely steep that curve is compared to an isothermal, constant temperature process. Because the system can't pull in any ambient heat to replace the energy it's spending on expansion work, its internal pressure and temperature just plummet much faster. It's a really satisfying visual confirmation of the math we've been talking about. Bringing it all back home to your everyday chemical reactions, we classify them based on that enthalpy change. If the final products have lower enthalpy than what you started with, the system dumped heat outward. That's an exothermic reaction, a negative delta H. It feels like a little space heater. But if the products end up with a higher enthalpy, the system actively stole heat from its surroundings. That's an endothermic reaction, a positive delta H, and it feels exactly like cracking a chemical ice pack. It is all about tracking where that energy goes. We have covered an immense amount of ground today. You now know how to calculate the exact flow of heat and work, and you've seen the first law's absolute guarantee that energy is always conserved. But that leaves us with one massive lingering question. If energy is just endlessly shuffling around in perfect balance, why is it so easy to scramble an egg, but utterly impossible to naturally unscramble it? What actually dictates the irreversible forward direction of spontaneous events in our universe? Think about that, because it's exactly what we'll be tackling next time. Thanks so much for joining me on this explainer.